think I will start now, and Jörg, please check if others
Yeah.
are still coming in. Hello and welcome everyone to the 32nd Merlin webinar. This time it's about integrating ecosystem services into cost-benefit analysis for freshwater restoration. And this time it's also a little bit different because we have 3 speakers. So the first one is Nicolas Grondard. He is a researcher at the Earth System Global Change Group in Wageningen University, and he's conducting research on ecosystem accounting, ecosystem assets and service modeling and evaluation, with a focus on agri-environmental policy and freshwater ecosystem restoration. And then we have Sien. She is currently doing her PhD at Deltares and Wageningen University. She is specialized in embedding ecosystem services into cost-benefit analysis of nature-based solutions in freshwater systems. And our third speaker is Isabell, and she is a research associate working on integrating ecosystem services into CBAs of infrastructure planning at the Federal Institute of Hydrology in Germany. And because we have 3 speakers, also the schedule is a little bit different than normally. So Sien will first introduce CBA in general and then talk about the funding gap. Then Nicolas will take over and talk about the Merlin integrated modeling framework. Then Sien will introduce the Dutch Rhine case study. And finally, Isabell will talk about embedding of ecosystem services into waterway infrastructure planning in Germany. This all should take approximately 45 minutes, and after that we have 15 minutes, or to all who have more time, we could also go over the 1 hour. Okay, and with that, I immediately give the floor to Sien. Just one more thing, if you have any questions, please write them into the chat so that we can ask this to the speakers afterwards. And please also maybe write a name to whom you would address the question. Thanks a lot, and Sien, the floor is yours.
Thank you, Astrid. Well, before we start with this whole session, I thought it would be wise to just, to those maybe not very familiar, talk really shortly about what a cost-benefit analysis is and why you should want to do one. So just real quick, cost-benefit analysis very simply is investment costs of a project or a policy compared to the welfare effects, all of those expressed in monetary values, in our case, euros. This is essentially an analysis that consists of a number of steps, starting with the problem analysis, describing expected developments against in a baseline situation, comparing different options, and then see, identify, quantify, and monetize effects and costs of those options. Then we do a bit of sensitivity analysis, and in the end, calculate everything back to the present value. The question ultimately a social cost benefit analysis tries to answer is, will a project increase the social welfare? So will the cost for society outweigh or weigh up against the benefits of society? Is there an investment rationale? This also helps in selecting the optimal alternative between a range of options. And ultimately, experiences are also that doing such an assessment helps in increasing the transparency in the decision ultimately made, as well as offer support in any dialogue that are to be had with stakeholders, because you are quantifying and identifying effects for a wide range of beneficiaries or cost carriers. Now, real quick, for those of you not familiar, we have in Europe quite a lot of plans for restoring our nature, our ecosystems, our water systems. And at present, for example, the EU biodiversity strategy is expected to cost, if we want to meet those goals, 55 billion a year. Current spending levels are not even half that. We know that the majority of the money currently going into restoration is public and will probably also remain public. But still, we also need to find more sources of funding outside the current budgets being used, be it public or be it private. So cost-benefit analysis will help you identify where potential opportunities are for finding co-funding. And it's also good to know that many investors, both public, which we'll hear Isabell on later, as well as private, generally require, especially for larger investments, a cost-benefit analysis to be made. Now, in the recent years, there's been a lot of attention for this topic, a bit more general. So for nature-based solutions and nature restoration, how do you do the economic rationale, the cost-benefit analysis? How do you get financing? But there's still quite limited experience and also tailored guidance specific to freshwater restoration. So that's really what we have been working on in Merlin in the last few years and what we'll be discussing with you today. To start with Nicolas.
Thank you, Sien. I'm going to share my screen now. Yeah. All right, good. Good afternoon, everyone. So I have the pleasure to present the Merlin modeling workflow, which is being developed by a team of hydrological modelers from ICRA and environmental economists from Wageningen University, collaborating in the Merlin project. So as mentioned by Sien previously, we need to mobilize more public and private funding for restoration. And to reach this aim, it is crucial to quantify and value the benefits that society derive from ecosystems restoration. Now, when it comes to freshwater ecosystems, it is a quite challenging and complex task because it requires very detailed hydrological hydraulic modeling with a lot of data inputs on land cover, land use, hydrology, and socioeconomic activities. As a result, many ecosystem services are often overlooked in cost-benefit analysis of freshwater ecosystem restoration, and therefore benefits and trade-offs of intervention, impacts on economic sectors are often not well understood. The Merlin modeling workflow aims to address this problem by making accessible a simple modeling tool that allows to model the effects of restoration on man-related water-related ecosystem services, and a workflow that can be applied to any water catchment in the EU, thus relying on EU datasets. The tool is being tested on 5 Merlin case studies with the aim to link cost-benefit analysis to the mobilization of public and private finance for restoration. So the Merlin modeling workflow models the effect of 4 restoration measures on ecosystems. So these 4 restoration measures are peatland reweighting, floodplain reconnection, channels remeandering, and riparian buffers. Then this modeling workflow models how those restoration measures impact ecosystems, and in turn, how it have effects on 4 ecosystem services: water purification, drought mitigation, flood mitigation, and carbon sequestration. And in the end, the monetary benefits we obtain from these 4 enhanced ecosystem services. It has a hydrological model component that provides variables used to assess ecosystem services, and a monetary valuation component that puts a monetary value on these ecosystem services flows. So first, the hydrological model components. So we use SWAT Plus for that. In a nutshell, SWAT Plus allows to model how water moves through a water catchments, depending on of course, the composition of the catchments in various ecosystems: forest, crops, urban, the slope, elevation, the temperature, precipitation. All these affects how water moves through the landscape and the water flows in the rivers, and so on. So with this model, we get some essential variables simulated by the model, like river discharge and nutrients and sediment flows. And these variables are used to quantify and value ecosystem services. So let's have a look at how it works for modeling flood risk and the effects of ecosystem restoration on reducing flood risk. So the hydrological model simulates the probability of a peak river discharge without restoration measures. You see here a simplified example with a peak river discharge probability of 10%. Before restoration, that is connected to a certain flood event. put on a map as a flood extent and flood depths. You see here the different meters of the flood depths. Without restoration, this flood event has a 10% probability of occurrence. Then the hydrological model simulates the effect of the restoration on the peak river discharge. We expect that with restoration, the water buffering capacity of the ecosystem is going to be increased. And so the peak river discharge probability of having such a high discharge is going to be reduced, for instance, here from 10 to 8.5%. And in turn, this will reduce the probability of this same flood event to take place. The next step then is to translate this reduced flood risks to a reduced flood economic damage. To do this, we relate the flood depths to a percentage of damage using flood depth damage relationships from the literature. So here, for residential land use, a flood depth of 1.5 meters leads to a damage of 50% of the land use economic value. So we multiply this damage percentage by the economic value of the affected land use, indicated by a land cover land use map, and we obtain a reduced economic damage thanks to the flood risk reduction. So now let's have a look at the modeling of the nutrients retention service. So nutrients retention takes place in land, in terrestrial ecosystems, as well as in the water catchment, in streams and lakes. Several processes are involved in nutrients retention: uptake in vegetation and sediments, denitrification in anoxic conditions. Restoration is expected to enhance the nutrients retention by increasing water residence time and channel floodplain connectivity, which favors those retention processes. SWAT Plus allows to model nutrients flows through the catchments, from nitrogen inputs, for instance, through fertilization or atmospheric deposition, phosphorus as well with fertilization, up to downstream exports of those nutrients. So nutrient retention is calculated with the aid of this hydrological model for each terrestrial ecosystem unit in the catchment and for each river segment. And by quantifying the nutrient retention for both the baseline and the restoration scenarios, one can quantify the effect of restoration in terms of additional nutrients retention, in terms of nitrogen or phosphorus retained in the catchment. To put a monetary value on this service, we adopt a replacement cost approach based on Lanotte and al. So this approach assumes that the value of the nutrients retention service equals the cost of an alternative solutions that would replace the service in case it was not provided by ecosystems. In this case, the alternative solution is a constructed wetland, which is dimensioned to provide exactly the same amount of nutrients retention as the ecosystem. And the constructed wetland area is determined to provide exactly this same service. It is then turned into investment and operation costs based on cost functions from the literature, and this provides us the value of the nutrients retention service. While in this replacement cost approach, we assume that if ecosystems would not provide the retention service, society would be willing to pay for an alternative solution. That is, we assume that there is a societal demand for the nutrients retention service. To check if this assumption holds, we propose to use the Water Framework Directive water quality status of water bodies in the catchment as a starting point. If water quality in a river or lake does not reach a high quality status for nitrogen or phosphorus, then we consider that there is a societal demand for improving this water quality, and therefore that society will be willing to pay for the alternative to the service. That is the constructed wetlands. On the contrary, if a river or lake already achieves a high quality status for nutrients, then there is no demand for the service and no willingness to pay for the alternative, and therefore the value of the service is considered to be zero. We see here an example of this approach with the forced catchment in Scotland, which is one of the Merlin case studies on which we are testing this tool. The yellow points that you see here indicates water bodies with a moderate quality for phosphorus, whereas the blue and the green points indicate a good to high water quality. So in this case, we consider that only ecosystem located upstream of the yellow points are service providers. It is also recommended to compare the monetary values obtained with this method with other estimates, if available in the literature, for instance, from willingness to pay studies, willingness to pay for high water quality, or existing estimates of the societal damage cost of nutrients pollution. So we are making this modeling workflow an accessible tool through QGIS plugins that can be run by people with knowledge and skills in GIS. And we are also preparing training materials that will form a specific module in the Merlin Academy. So for those who are not familiar with the Merlin Academy, you can look it on the website of the Merlin project, and it's a complete suite of training modules on various topics related to freshwater ecosystem restoration. So that will include also how to run this modeling workflow. And there will be also coming soon a report from Merlin on this modeling workflow and how to use it. It will be a user guide on how to apply this workflow using the QGIS plugins. And lastly, we are also working on a more general guidance document on cost-benefit analysis in freshwater ecosystem restoration. It will be based on the application of the Merlin modeling workflow in the 5 case studies, but also includes other CBA works that my colleague Sien and Isabell are going to introduce in the next presentation. And that was the end of my presentation. Thank you, and back to you, Sien.
Thank you, Nicolas. And here we are. I would like to tell you a bit about the work I've been doing on applying the principles just introduced a bit by Nicolas to a specific case study in the Dutch Rhine. In the previous century, throughout all of Europe and the world, we have done some far-reaching modification of floodplains and rivers. We have straightened them for navigation. We've put dikes on the banks to improve agriculture in the floodplains, and there's all tons of barriers for hydropower or navigation purposes. And in the present day, we're still dealing with the consequences of those interventions, as well as being presented with new challenges, such as increased flood and drought probability due to climate change. Against this backdrop, there's stronger support for more integrated management of these ecosystems, as well as to support uptake of nature-based solutions. For example, in Floods Directive, the Biodiversity Strategy, and other types of directives in the EU. But there is still a lack of implementation. And we don't only see that in practice, we also see that in all studies that are reflecting or working to support decisions being made in river and floodplain management. As mentioned before, these tend to focus mostly on the primary effects of interventions, and these interventions are generally for specific sectors, so very siloed approach. If we do want to have a more integrated river and floodplain management strategies, as well as increase the uptake of multifunctional solutions such as nature-based solutions, we also need a wider scope in our assessment tools. Then another research gap that's identified is that there's still a lack of data on costs for nature-based solutions in particular. So the objectives of my study were twofold: to start by quantifying a very wide range of ecosystem services under different type of strategies in my case study, and look at trade-offs between them, but then also to review the impact of such a wider scope on the final cost-benefit analysis results. Hypothesis, of course, being that in a very strongly regulated system, a more integrated management would increase especially regulating and cultural ecosystem services. This work has been published this year. As well as that, with a wider scope in benefits assessed, we would expect a stronger economic rationale, in particular for multifunctional strategies, and this work is currently under review. The case study I'm talking about is the Rhine branches in the Netherlands. So the Rhine enters from the east from Germany and then immediately splits up into a number of branches. To the north, you can see the IJssel River or branch feeding into a very large inland lake, which supplies a lot of fresh water for agriculture and other functions. Some of the key challenges in this system currently is increasing riverbed incision. So there's not enough, or the sediments do not supply enough. So there's a lot of erosion of the sediment, as well as increasing probability of low flows. And this has shifted the discharge distribution towards the western branch and away from the northern branch, which has lots of problems for navigation, especially to the north, as well as freshwater provision. So the refill rate of that lake is going down, as well as reducing the connectivity between the river and its floodplain. So we're losing wet ecotopes, essentially. Then, of course, against this backdrop, we also have the need to meet Water Framework Directive goals, Natura 2000, and there's additional domestic nature policy goals to be met, as well as dealing with increased flood risk expectations under climate change. These challenges are currently being tackled in a so-called Room for the River 2.0 program. We had a following the Room for the River program in the early 2000s, but that's still very much in the early stages. So I identified two distinct strategies for these challenges. The first being resilient river, focusing really mostly on reducing impacts of floods and droughts. So there's part increasing the discharge capacity of the system by setting back dikes and developing flood side channels, as well as efforts to maintain the current riverbed level by doing annual sediment suppletion. There's no change in the use of the floodplains foreseen in this strategy. Then in the living river strategy, there's also a lot of attention for increasing the flood discharge capacity, but in a more natural way. So there's also dike setback, but also a system of interconnected permanent side channels, which are also expected to support the goal of restoring the riverbed level, additional to initial suppletion, to a former level, as well as converting agricultural land use to more natural land use in a sort of medium strategy, as well as fully abolish agricultural land use in an extreme scenario. I don't want to go into this too deep, but just to show you what are the main impacts identified from these interventions. So along a longitudinal perspective, these affect flood protection, navigation, and irrigation supply. If we look at it from this side, yeah, again, I don't really want to go into the details, but there's impacts on the nutrient retention capacity of the river, as well as the potential for specific ecotopes to develop, which relate to the habitat provision function. This has to do with how often and how frequently the floodplains flood. Then by making more room for the river, there's a provision of construction material, and of course, flood protection services provided. There's also an impact on groundwater levels, both within the floodplain and beyond the floodplain, which may affect crop production. And the change in land use, here on the left, we see the current situation, which is still largely agricultural function. If we were to change it in a very extreme scenario to a much more natural system, this would have impacts depending on vegetation management, biomass production and carbon sequestration, habitat provision, of course, recreation functions. I specifically looked at fishing and walking and cycling. And then there's impacts of landscape quality on property values, which we call amenity value of the landscape. Now, For each of those services, we identified concrete indicators to quantify and also connected stakeholders and beneficiaries. And then here you can see a spider chart on how the provision of these services changes depending on that floodplain river management strategy that you implement. The red line is sort of looking back a bit to the past, so an older configuration of the floodplains where we didn't do room for the river 1.0 yet. The gray area is the business as usual, the baseline. And as you can see, indeed, in the very green line, so the most natural system, essentially the supply of all ecosystem services is largest, with a major trade-off with agricultural production. Now on to what we're here today to discuss the cost-benefit analysis. So from all of those quantified benefits, we went on and monetized the majority of them in euros, as well as established the implementation costs. So that's both initial investment costs as well as the operation and maintenance phase for all measures taken to increase the discharge capacity, to manage the sediments in the rivers, as well as to develop nature. I would like to give one example so you can see a bit what's under this big black box of methods, is how we calculated the habitat provision function and in the next step how we estimated the bequest existence value of that habitat. So we start here with putting in data on the elevation throughout the floodplains. We calculated with hydrological models changes in the water level discharge relationship along the rivers. Connect those to discharge capacity and land use, and then you can get this inundation duration maps using the Deltares habitat model. This then gives us an idea of, in a given location, would we expect a more dry or a wetter ecotope? And that ranges from swamp to permanently inundated to maybe a wet grassland or a forest. What it becomes is depending on how you manage it. So will you keep cutting down everything? It will remain a grassland or not. So from that, we can get an idea of how many hectares per ecotope type do we expect. And we developed a policy achievement indicator by combining it with policy goals, which were set on the number of hectares required to maintain robust populations of desired species. So then you can indeed see that the degree to which these policy ambitions of our nature program are met range very strongly depending on these strategies. Now, you can monetize this by putting a willingness to pay on this conservation or degree of restoration of nature. This is a non-use value. So what are people willing to pay just to have that nature back, even if they do not intend to use it themselves? A general approach that is used if you don't have an excess amount of time is to use a benefit transfer function, building on similar analyses where people are being asked in very wide surveys what is their willingness to pay in Europe. So we're using this specific study, doing that for wetland conservation programs in Europe to derive a willingness to pay. The degree of restoration, to make an assessment of how much is being restored, for that we use that indicator I just discussed, so the policy target achieved. The resulting numbers per household are listed here, so ranging from 5 to almost 30 euros for the most extreme, most restored system state. Now, of course, we don't expect this value to be paid endlessly by everyone, so we adjust this for distance decay. So the farther away you live, the least invested you may be in restoring or maintaining that ecosystem. Now, the final results you can see in this figure here. The star in each figure shows the level of benefits needed to break even, essentially, to have the benefits be higher than the costs. So you can see that last living rivers, all agriculture abolished variant is the one that is most attractive from an economic point of view. So that one has higher benefits. The large majority of benefits is in green are the cultural services. So anything to do with flood protection, water regulating services is in blue, and dark green is much smaller. As well as on the cost side, you see that especially investments in costs in discharge capacity, dike setback, and developing side channels is most costly. I just wanted to highlight that in this case, if you only look at the direct benefits, which was done in the official cost-benefit analysis of this program, so that's only agricultural production, flood mitigation and navigation, the resilient river strategy would come out best. If you take account also of the cultural services, the preferred alternative shifts to that living rivers alternative. And you can also see that at first there is not an economic rationale, so the benefit cost ratio is lower than 1, but in the case where you incorporate all benefits, it becomes higher. So, to conclude, the way that we are currently doing our cost-benefit and assessments in practice essentially form a disadvantage to more nature-based strategies. And we can, if you do include it, this has the potential to shift the preferred alternative as well as increase the economic rationale. Well, as you can see, these results were strongly influenced by that willingness to pay for habitat provision. So we, of course, compared it a bit to what's happening in literature. And in that sense, there's a very wide range found in literature throughout the world. On average, it's around 70 euros. So we calculated, to be sure, also the break-even point for that extreme living rivers restored scenario. So at present, the willingness to pay was calculated at around 30 euros. If it is more than 19.5 euros, then there would be a positive economic rationale. So this to us seems feasible. Well, just to get a bit of an understanding, this approach that is presented here will inform and inspire the current ongoing planning process of Room for the River 2.0 in the years to come as well. And generally, this approach and the findings are also transferable to other regulated river deltas. And that's it for me. Now the floor to my colleague Isabell. Thank you.
Thank you so much, Sien. I'm very happy to be here today and present you. I hope you can all see my screen. Yes, hello everyone. I'm glad to be here with you, and I will present you a little bit more about current developments in Germany on integrating ecosystem services into infrastructure planning and projects on the ground, specifically on the federal inland waterways. I think my colleague Sien mentioned already a lot of the same problems we are also facing in Germany. So of course, transforming most of our larger rivers into major waterways has caused them to be highly modified. Over 90% of our floodplains have been degraded or lost, and less than 8% of our surface waters are actually in good ecological status. At the same time, we're also facing increasing climate damages. Between 2018 and 21, we had 18 billion euros in damages, and half of that was just from a single flood event. At the same time, we see that there's a change in user demands and societal values actually for our rivers and ecosystems, with more demand for recreation. Tourism is gaining more weight in our management and also in the public. But at the same time, navigation still is the major player and major sector on our rivers and waterways specifically. And doesn't fully consider yet these challenges that have taken place. So climate, CO2 mitigation targets we have on a European and national level, but also that change and shift, and also a call from decision makers that call for more integrated assessments and economic valuations of ecosystem services and environmental damage that result in specific types of planning. But luckily, at the same time, we have an exciting window of opportunity right now. The major federal infrastructure and transportation plan that we have is currently being updated, which also brings a new expanded methodology of the cost-benefit analysis tool that we have, and an opportunity to more comprehensively integrate ecosystem services and these considerations. And also our Federal Waterways and Shipping Administration has a new mandate, and by passing a law in 21, that also warrants more weight for restoration and more sustainable water management. I would like to give you short an overview of actually how on an operational level projects are planned and implemented in Germany. On the left, you can see our waterways that have been prioritized previously on a strategic level. And then on an operational level, we implement similar projects than my colleague from the Netherlands just mentioned. We have an opportunity here to integrate two specific points, monetary, non-monetary values of ecosystem services, specifically when we compare these different project variants and scenarios, to have a more comprehensive view actually and reduce user conflicts that we have, consider more societal benefits and the increasing value of ecosystem services. For this, due to this cause, there's an extraordinary project that just finalized but still is not finished, is the research and development project Ambrose at my institute in Germany. And specifically, it looked at identifying a standardized assessment procedure to compare ecosystem service value changes under different measure scenarios and project variants to provide actually to the Federal Shipping Administration and the Ministry of Transportation a more comprehensive standardized approach that looks at all the values that have yet been excluded. And this was done by selecting 15 ecosystem service indicators that are directly linked to our rivers and waterways specifically, and follows a very similar method that the methodology that Nicolas just outlined. So first, also they were assessed on a biophysical parameters, and then with socioeconomic methods and values. There's not enough time to show you this, but on the right-hand side, you can see the individual monetary values that were identified for most of these ecosystem services. Just down below, you see an abiotic value, navigability. We see this more as a natural capital provision and not directly as an ecosystem service. And it was not monetized on the side of ecosystem services because it's already integrated in a federal infrastructure plan so that we don't have the risk of double counting. And the process looks again similar than in the other projects in Maryland. First, different project variants that are undertaken in Germany's waterways were then selected for the different projects that we had. And then on the right-hand side, you can see how this actually looks like. This is the QGIS plugin tool from Ambrose, specifically on a dike relocation and floodplain restoration project, how the crop provision and here depicted through the soil quality rating changed under different scenarios, which is also very similar to an approach that was done in another project, the RESI project, where different ecosystem services and measure scenarios were also quantified, but the scale was different. So instead of 100 by 100, it was 1000 by 1000. And the values were not monetized, which differed to Amber's. So specifically, Amber's offers actually both quantitative results, but also for the ecosystem services and the different projects and their scenarios, monetary values if possible. But all of this is very dependent on the available data, which is a huge challenge still. There's also issues of methods still and a lot of open questions that are still being worked on to be answered to operationalize this fully. Here I would like to just show you how this QGIS tool actually looks like that will be used by the federal administration here. Of course, it's very important always to look at the right assessment time frame and the project cycles. There's different discounting rates that you could choose that greatly would influence then, of course, the results and the individual ecosystem services for your location. All of this was piloted also for different project variants along Germany's waterways. Right now, the final report and guidebooks are compiled before different more specific piloting will commence. And the exciting thing is that this is really per request and also driven by the administration and the ministry. So there's a great interest and a realization that with new laws and mandates, it is actually beneficial to integrate this and can offer a lot of benefits. Yes, but also CBAs are integrated on a strategic level. So here you can see the overview of how actually projects are selected and then prioritized in federal transportation plans that are renewed every 10 to 15 years in Germany. There are 4 modules that equally weigh to then prioritize projects, which are of course ultimately made on a political basis, but these 4 modules provide a great deal of decision-making support. So they're really important. On the right-hand side, you can see some of these CBA components. There's also environmental components highlighted in green here that are already included. But some of the values are outdated, such as the carbon data. And also they don't fully integrate ecosystem services. But on the right-hand side, you can specifically see 3 indicators from Embers that were already selected that could match then and be integrated potentially into this plan. And there's also a more openness to integrate further ecosystem services as long as they're able to monetize them. Other ecosystem services could be then integrated more comprehensively also in the strategic environmental assessment for non-market values. Here, I just wanted to give you a brief insight also how this actually looks like in Germany. So here's one project that doesn't fully focus on restoration or anything. It's a optimization for shipping capacity load on a stretch of the Rhine. And I wanted to show you how this actually looks like. Here, a cost-benefit ratio of 13.7 was calculated. Everything above 1 in most cases is considered beneficial, so this is a very good scenario. And there's also a ranking that is done in a quantitative way to then assess the environmental potential impacts of that project. But on the right-hand side, you can see a study commissioned by the Ministry of Environment. Since the current federal infrastructure plan is under review, this is actually for federal highways, where you could see that the results from the previous plan in 2012 has a very different result compared to today's values. So due to higher greenhouse gas emission costs that are expected to increase, and also rising construction costs, a lot of these previously deemed very good cost-benefit ratio projects are actually not that beneficial anymore. And similar results are expected also for projects along Germany's waterways. So overthinking this status quo assessment approach and integrating the AMBIS module and approach on an operational and strategic level makes a lot of sense from a scientific standpoint. Yeah, so the exciting thing is really there's a lot of entry points and a lot of interest. One is what I already mentioned, the expanded operational mandate due to the new law in 21 requiring the Waterways and Shipping Administration to really give a legal backing and a greater weight to environmental considerations, and thus also ecosystem services. The new infrastructure plan, and a whole suite of research projects that are underway right now in Germany. Yeah, all of this, what I find very exciting is that the strategic level and operational level are really working together in a way through the AMBERS project, that there's a focus on trying to bring both the assessment tool for projects on the ground, but also on a strategic level. And this is done together with different consultancies, researchers, and practitioners, and dialogue in Germany. And yeah, we're excited to see what this year and next year will bring. Just finally, to briefly sum this up, my colleague Sien mentioned this already. There's a lot of policies on a federal and a European level where there's already CBA and ecosystem service valuations, either mandated or highly encouraged, including the biodiversity strategy, but also the EU environmental economic accounting, which now requires ecosystem services actually, and a monetarization soon for all member states. And also in Germany, there's much more synergies that could be taking opportunity of. Altogether, I think there should be more and could be more science policy exchange, even though there's already a lot of dialogue happening, and an improved collaboration across all agencies involved. to really then bridge these knowledge and data gaps that we still have to compare different measure types. Often a key barrier is that we don't have the data actually before measures to then compare before and after scenarios, or the scale is too fine. So there's still a lot of questions and methods, especially for socioeconomic assessments, that we can improve on. And now we're excited to enter the floor to all the questions you might already have posted in the chat. And thank you so much for your attention.
Thank you to all three of you for these very interesting presentations. We have already a few questions. The first one was by Alejandro, and I think it's meant for Nicolas. He said, I assume it can be nitrogen or phosphate or both for the target limiting nutrient. So it's just a yes or no.
Yeah, it is right. It's like that. It's for you can select the constructed wetland to be dimensioned either based on the retention of nitrogen, the retention of phosphorus, or both, depending on your specific context. Yeah, indeed.
Okay, thank you. Next question by Evgenia. She asks, and this goes to Sien, I suppose, ecosystem service indicators have been selected from the CITES inventory or from any other source?
Yes, thank you. I mostly used actually a list of ecosystem services developed by the Reform project around 2015, which were more targeted to ecosystem services related to river restoration. So that's a valuable source to have a look at, I would say.
And do they somehow are they the same as in this CITES, or is this
that they just fit a bit better too, because CCAS is very broad, so also for terrestrial systems, and I just found that this worked a bit better for river or water related ecosystems. But I mean, there's a lot of overlap, but well, just for me this worked a bit better, the list from the Reform project. Yeah.
Hope this answers the question of Evgenia. Next question is also to you, Sien, from Maya. She wanted to know what are some of the compensation and community involvement mechanisms for land conservation along the floodplain from the current agricultural activities. How does that factor into the cost estimate of restoration? And what would the projected timelines be for a partway and 100% conservation from e.g. to compensation land, agriculture.
Yeah. Well, thank you for that question. I think there is a bit of difference between doing a cost-benefit analysis like the one I presented at a sort of program level. It's quite strategic, and between doing it at a more project floodplain local level. That being said, so in this case, it wasn't actually recommended from a very theoretical cost-benefit point of view to look into concrete compensation mechanisms, because it's generally recommended to look at the opportunity cost incurred. And opportunity cost basically mean how much revenue is being made from the agricultural use at that stage, without looking into the actual compensation that you would do. So I didn't do that, although I recognize that in reality, in practice, of course, you would need these kind of mechanisms involved. And I would also definitely recommend that in a local, more specific cost-benefit analysis. Regarding the timeline, also I didn't look at that part specifically. So in general, for the entire project, I used an implementation timeline of current until 2050, sort of gradual implementation. But of course, in practice, this would take quite some time because you would have to buy out and or compensate and maybe wait out lease contracts and everything. I hope that answers your question. It's not a... Yeah. Thank you.
Maya, if this doesn't answer your question, you could. Oh, it does. Okay, cool. Thank you. And the next two questions are to Nicolas from Elma, and he wants to know for which scale is the Merlin ecosystem and CBA model, ecosystem service and CBA model developed and does deliver sound results. And the second one is to which stage of project cycle do you recommend to apply the Merlin model or to guide project management decision taking?
Yes, thanks for the question. At which scale it is developed? It's for large catchment scale, I would say. That's where it would apply most. Whether it delivers some results even at this scale is something that we are also discovering and testing in the Merlin case studies. And in at least one of the case studies, we are busy comparing the outputs from this modeling workflow using EU data as planned, as default data, to the same workflow applied used with more local data on land use, land cover, and socioeconomic data. Because apart from the model itself, the type of and the resolution and thematic accuracy of the data you use as input is of course going to have a lot of influence. So this is something we are busy doing to gain insights on the robustness of the results you get using different data inputs with the model. And regarding the question of which stage of project cycle, I would recommend to apply this tool more as a kind of pre-screening screening stage of strategies. Like if you want to have a first ID or first order ID of the different ecosystem services benefits that you would get by applying a certain restoration plan. That's I think where the model would suit best. Then when you have taken the decision to enter more into the design of the program and you have to work at a much more detailed and local scale, probably other type of tools, more based on local data and adapted to the specific context of the catchments, will be needed.
Thanks a lot. Elmar seems to be satisfied as well, so we can move on to Alejandro. I don't know whether he's still here because he said he had to leave earlier, but I still want to ask his question here. So perhaps you have calculated this already, but for each euro invested, how much and with which uncertainty range is gained in co-benefits and when in the timeline? So I know,
Yes.
Sien, you have already answered this in the chat, but maybe people would want to.
Yeah, certainly. Yeah, so this was an add-on to his earlier question on the existence value being such a very big benefit compared to the others. So he's also asking about main uncertainty bands or key sensitive parameters. Yeah, so to get back to that first question on what is the main uncertainty in that estimate of willingness to pay for bequest existence value. It's quite difficult to determine how the degree of restoration in the system affects the willingness to pay and how this is reflected in that benefit transfer function based on the literature. So that's quite uncertain. So how do you make an assessment of how much is a system restored and how does that compare to a current situation and how does that affect the willingness to pay, etc. That's not very well studied yet. And then, of course, a very important and very uncertain factor is how large is the market size. So how many people are you going to expect will be willing to pay this value? So what I did now was base my distance on earlier research for willingness to pay on water quality in lakes in the Netherlands. So it's based on the Netherlands, but the topic is a bit different. So I would expect maybe that for preserving this river nature, which is really quite rare in the Netherlands, it might be a bit bigger than. So I assume this would be a conservative estimate what I use now. And the same goes for the form of the distance decay function. So are we assuming this willingness to pay is just linearly reducing with distance? But there's also research showing that it's more related to how close are substitutes. So if you live very close to another river, you probably won't be willing to pay for the one further away. So ideally, you would also incorporate those things. Now relating to the question on uncertainty bands, I didn't really calculate those, but we do have an ongoing master student of mine running a Monte Carlo analysis on other effects as well, but this one as well, to really test which are the biggest uncertainties and how do these affect the band. So I hope that answers the question. Maybe the final question, I didn't calculate a return on investment yet. So a return on investment is basically how much for each euro invested are you going to get in benefits. And when, well, the when is not really something that we do in a cost-benefit analysis, because we always want to, calculate it all back to that one value in time. So we can discuss that later on if you're interested. Thank you for the question.
Alejandro, are you satisfied? Or maybe he has left already. So then we have a final question by Gavi. And this is, are these methodologies applicable to just big deltas or big rivers, or can they be used for smaller river sections as well? I think this goes also to Nicolas and Sien.
Shall I take it? Yeah, as I said previously, it's more for large catchments that this modeling workflow is to be applicable. Having said that, if you have the right level of detailed and spatial detail in your input data, you will get results that may be useful as well for smaller restored, smaller river sections, let's say. But there are two dimensions in this: is whether you want to model, what you want to model, and at which scale you want to see the results. So if you want to model just a small action, a small restoration of a small segment of river, it's probably not going to be reflected in the modeling outputs of a SWAT plus model calibrated for large catchment. So in this sense, I think if you are really speaking about modeling the effects of local restoration measures, you would need other type of tools and assessment methodologies, and probably use more monitoring program, like was done also in the Merlin case studies. So you can also have a look about the monitoring results of the Merlin case studies on this for this kind of assessment. I hope it answers the question. Maybe Sien, you want to add something on that?
Yeah. Well, maybe just that monitoring, of course, doesn't really help you in ex-ante analysis, so before the project has been done. But this is also my general recommendation, is that it's not one-in-one applicable to smaller scale. It does need some thinking and maybe changing of some tools or methods more based on local data. Yeah.
But are you maybe aware of any research going on in smaller catchments?
I'm aware
A lot of examples, yeah. Oh, sorry. There's a lot of examples, of course, of projects where cost-benefit analysis have been made using all sorts of data. It's just that I think we have really tried to focus a bit our work on catchment scale, strategic level modeling and economic assessment. But there are, in grey literature, a lot of examples for more local projects that can be used as a starting point. Yeah. Isabell, did you want to add something?
Yeah, I mean, we do have some research in Germany also, and methods need to be adjusted to very small scales. And like Sien always also said, it's sometimes very hard then to really correlate the effects that you see with really the measure in ecosystem service changes. And to monetize that, it's also really difficult. So in Embers, we also looked at that a lot. But I think because sometimes also it's very context specific, and then also you want to maybe use data from other areas to transfer to very local context. That doesn't always work, even with benefit transfers. So yeah, but there's definitely a lot of examples out there, but especially for smaller scale, there's more data gaps, I think, that we see, at least in Germany. More knowledge gaps that still are to be filled.
So a small Merlin project is needed. Thanks to all of you for your answers. Do we have any further questions? If you have, you can unmute yourself and just ask it. Nope. Okay, then, yeah, thanks again for these interesting presentations. The Merlin webinars will now go on summer break, and we will be back in September with Daniel Sorel, and he will talk about the blue targeting forestry planning tool. Yeah, and you will see our advertisements soon, somewhere at the end of summer, so that you don't forget about this webinar. Thanks a lot again to the speakers. Thanks for your attention and enjoy the rest of your afternoon.